Supernovae, the catastrophic explosions that mark the violent death of the universe's biggest stars. For centuries, we've pictured these blasts as the final, irreversible act of a star's life. One bright flash, and the star is gone, leaving behind a neutron star, a black hole, or nothing but a cloud of stardust. But what if I told you that the universe has been tricking astronomers for decades? What if some of these supernovae we observe are not deaths at all, but near-death experiences, cosmic illusions that burn as bright as a real supernova, yet leave their parent stars completely unbroken? Today we're diving into one of the most mind-bending mysteries in modern astronomy: the false supernova, also known as a supernova impostor. These are not the end of a star, but a spectacular, violent outburst that challenges every rule we have for how massive stars live and behave. By the end of this video, you'll be able to spot these cosmic fakes, understand why they happen, and see how they're rewriting the story of the most extreme stars in the universe. Let's start with the basics. What even is a false supernova? At first glance, it looks identical to a real supernova. It suddenly flares up in a distant galaxy, becoming millions of times brighter than it was before, shining with a light that can outshine entire star systems for weeks or months. Early astronomers, even some of the greatest minds in 20th century astrophysics, would log these events as genuine supernovae, marking them as the death of a massive star. But here's the twist. When astronomers point powerful telescopes back at that same spot, years later, the star is still there. It didn't explode into oblivion. It didn't collapse into a black hole. It just had a really bad day, shedding massive amounts of its outer layers into space before calming down and going back to life. That's the defining feature of a false supernova. It mimics the brightness and appearance of a terminal stellar explosion, but it is non-terminal. The star survives this simple fact, makes supernova impostors some of the most confusing and fascinating objects in astrophysics, because they break the pattern we've built for how massive stars end their lives. To understand false supernovae, we have to talk about the stars that create them, luminous blue variables, or LBVs. These are not ordinary stars. They are the heavyweights of the cosmos, rare ultramassive stars that can weigh 100 times or more the mass of our Sunday. They burn ferociously hot and bright, with luminosities hundreds of thousands to millions of times greater than the Sunday. Because they're so massive, they live fast and die young, usually only a few million years, compared to the Sun's 10 to billion-year lifespan. But LBVs have a quirk no other star has: they are incredibly unstable. Their gravity tries to pull all their material inward, but the intense radiation pressure from their core pushes outward so hard that it often overcomes gravity. This constant battle between gravity and radiation creates wild, unpredictable changes in their brightness, size, and mass loss. Most of the time, this instability is mild, causing small fluctuations in light. But sometimes it spirals out of control, triggering a colossal eruption that we see as a false supernova. Scientists still don't fully understand the exact trigger for these giant eruptions, but the leading theory points to the Eddington limit. Named after British astronomer Arthur Eddington, this limit is the maximum luminosity a star can have before radiation pressure becomes so strong that it overwhelms the star's gravity and starts blowing off its outer layers. LBVs live so close to this limit that even a small disturbance, a slight increase in core energy, a shift in internal convection, or a gravitational nudge from a binary companion star can push them over the edge. When that happens, the star can no longer hold itself together. It erupts in a brilliant outburst, ejecting huge chunks of its atmosphere into space at speeds of thousands of kilometers per second. This ejected material slams into the surrounding space, creating a bright, glowing cloud that looks exactly like the debris from a supernova explosion. The star's brightness spikes to absolute magnitudes between -11 and -14, making it as bright as the most luminous stars in the universe. But crucially, the core of the star remains intact. It doesn't collapse, it doesn't detonate. It just loses a lot of mass and calms down, often taking decades or centuries to return to a relatively stable state. Now, let's compare a false supernova to a real supernova so you can see the difference clearly. A true supernova is a core collapse event. When a massive star runs out of nuclear fuel, its core can no longer support its own weight. It collapses inward in a fraction of a second, creating a shock wave that blasts the entire star apart. This is a one-time, catastrophic event. The star is completely destroyed, and nothing like its original form remains. True supernovae reach much higher peak brightness, often above -17 absolute magnitude, and their ejected material moves at tens of thousands of kilometers per second, far faster than the material from a false supernova. Their spectra show broad, fast-moving gas lines, and after the explosion, there's no star left to find. A false supernova, by contrast, is a surface eruption. It only blasts off the outer layers of the star, leaving the core and most of the star's mass intact. The ejected gas moves much slower, and its spectrum shows narrow hydrogen lines, a signature of low-velocity material that tells astronomers this isn't a full-scale explosion. Most importantly, the star survives, and astronomers can observe it long after the outburst fades. This distinction wasn't clear until the late 20th century, when powerful telescopes like NASA's Hubble Space Telescope let us peer back at these exploded stars and find them still shining. The most famous example of a false supernova is the Great Eruption of Eta Carinae, a monster star system located about 7,500 light-years from Earth in our own Milky Way. Eta Carinae is one of the most massive and luminous stars we can study up close, weighing more than 120 times the mass of the Sun. In the 1830s and 1840s, astronomers in the southern hemisphere watched in awe as Eta Carinae brightened dramatically, becoming the second brightest star in the night sky, brighter than every star except Sirius. For nearly 20 years it blazed like a supernova, leading 19th century astronomers to believe they were watching a star's final death throes. But then, it started to fade. By the early 20th century, it was too dim to see with the naked eye. Decades later, when astronomers studied it with modern telescopes, they found Eta Carinae was still there, surrounded by a beautiful bipolar cloud of gas and dust, called the homunculus nebula, made of the material it had ejected during its great eruption. The star had lost roughly 0.16 times the mass of the Sun, enough to make several planets the size of Earth, but it had not died. This was the first time scientists realized that a supernova-like event could leave a star alive, and Eta Carinae became the prototype for all false supernovae. Even today, it remains the only false supernova progenitor close enough for us to study in extreme detail, making it a treasure trove for astrophysicists. Eta Carinae isn't alone. Astronomers have identified dozens of other false supernovae in distant galaxies, each telling the same story. A massive LBV star erupts, mimics a supernova, and survives. Some well-known examples include SNEN 1961V in galaxy NGC 1058, SN 2008S in NGC 6946, SN 1997Bs, and SN 2010DN. In every one of these cases, astronomers initially classified the event as a real supernova, only to reverse course years later when they spotted the original star still shining. One particularly dramatic case happened in 2004, when an amateur astronomer discovered a bright outburst in galaxy UGC 4904. It was labeled a supernova, but 2 years later, the same star erupted again, this time as a real supernova, SNN 2006 JC. That event taught us a critical lesson: false supernovae can be warnings. An LBVs giant eruption might be a sign that the star is running out of time, shedding mass in its final unstable years before its true core collapse supernova. The discovery of false supernovae has forced astronomers to completely rethink our models of massive star evolution. For a long time, we thought massive stars follow the simple path: burn fuel, expand, collapse, explode as a supernova, and leave a compact remnant. But LBVs and their false supernova eruptions add a wild, unpredictable chapter to that story. These massive eruptions are not just random fits of anger from stars. They are a vital part of how massive stars lose mass. Stars as heavy as Eta Carinae can't hold on to all their mass forever. If they didn't shed layers through eruptions, they would become so unstable that they would tear themselves apart long before their core ran out of fuel. False supernova events are nature's way of letting these extreme stars vent their excess energy and mass, allowing them to live long enough to reach their natural end as a real supernova. This mass loss also shapes the space around the star, creating dense nebulae that become the building blocks for new stars and planets. In short, false supernovae aren't just cosmic illusions, they are key players in the life cycle of the universe's most powerful stars. NASA has played a central role in unlocking the secrets of false supernovae. The Hubble Space Telescope has given us crystal-clear images of Eta Carinae's homunculus nebula, letting us map the ejected material and measure its speed and composition. The James Webb Space Telescope, with its infrared vision, peers through the dust clouds that hide LBV stars, revealing the stars themselves and the details of their eruptions. The Kepler Space Telescope and other transient surveys have discovered hundreds of stellar outbursts, helping astronomers build a catalog of false supernovae and learn how common they really are. Before these missions, we thought false supernovae were extremely rare. Now we know they are more common than we guessed, and they are a normal part of the life of the most massive stars. Every new observation brings us closer to solving the final mystery. What exactly triggers these giant eruptions, and can we predict when an LBV will erupt next? What makes false supernovae so special, beyond their trickery, is that they bridge two worlds: the quiet, steady life of stars and the violent, explosive death of supernovae. They show us that the universe isn't as black and white as we once thought. Stars don't just live or die, they can have near-death experiences erupting with the power of a supernova without meeting their end. They remind us that the cosmos is full of surprises, and that even the most well-established ideas in science can be turned upside down by a single strange observation. For astronomers, false supernovae are more than just a curiosity, they are a puzzle that pushes us to build better models, design better telescopes, and look at the universe with more open minds. For anyone who looks up at the stars, they are a reminder that the night sky is full of secrets, waiting to be uncovered. The next time you hear about a supernova being discovered in a distant galaxy, take a moment to wonder, is it real, or is it a fake? Is it a star's final goodbye, or just a dramatic outburst from a massive LBV, letting off some cosmic steam? Thanks to decades of research and NASA's cutting-edge telescopes, we're getting better at telling the difference. But there's still so much we don't know. We still don't have a complete theory for why these eruptions happen. We still don't know how many LBV stars are hiding in our galaxy, waiting to erupt. We still don't fully understand how these false supernovae shape the evolution of galaxies and the creation of heavy elements. Every new false supernova we discover is a new clue, a new piece of the puzzle that helps us understand the most extreme stars in the universe. The universe is full of illusions and mysteries, and false supernovae are some of the most captivating. They teach us humility, showing us that even when we think we have the cosmos figured out, it can still surprise us. They connect us to the grand epic story of stellar evolution, where stars are born, live unstable, lives erupt in brilliant fake explosions, and finally, die in real supernovae, seeding the universe with the elements that make life possible. As we keep exploring, keep observing, and keep asking questions, we'll keep uncovering more about these cosmic impostors, and in doing so, we'll understand more about our place in this vast, wonderful universe. Please like, comment, share, and subscribe to the channel.